Okay, let's get started. We will continue our discussion on what we can do and what we can't do with codes. In fact, most of everything, almost everything we do today will be what we can't do. We'll be getting better and better upper bounds on the rate delta. G. So begin with, let's recap. Let's recap from last. The two main things which we did were what we can do, the Gilbert-Washimo bound, and what we can't do, the Hamming bound. So let's just quickly. So what we can do is the GV bound. And in its most generality, it says if ND positive any positive integer, then there exists a code C in NKD2 code C such that 2 power k is greater than or equal to 2 power n by volume 2 n d minus 1. This is what we had. Okay, so you give me an NND, there will exist a code for which the k is so large, and this was just by the greedy method we saw. In your problem set, you will see that even the probabilistic method actually will fetch you this. You will have to do some sort of it won't exactly give, just the probabilistic method won't give you, you'll have to massage it a little bit and then you get this. We also saw if you don't, you can actually get the code to have a little more structure, you can get a linear code which has this property. And in the problem set, we gave a probabilistic construction for this in the class. In the problem set, you will see a greedy construction for the linear code. And actually it will do a little better than this. This n will get replaced by n minus 1, d minus 1 will get replaced by d minus 2. That's what we show in the problem set. And yeah, we have to do some integration. So this is the statement which we had proven. And in the asymptotic notation, that is R is greater than or equal to, what is this? R is greater than or equal to 1 minus H2 delta. That is, you can achieve R delta that satisfies this. This is the takeaway from the GV bound. And let's go now to what we can't do. The bound which we had talked about was something we talked about in the very first lecture. Is the Hamming bound. Also the packing bound. If C is a NKD2 code, then we must have that 2 power k should be less than or equal to 2 power n by volume 2n d minus 1. So many balls you should be able to. You can pack. If you put so many balls of this size, you cannot have more than. If you put balls of this size around each thing, it should still be less than the whole space because these balls are a disjoint partition of the. And the asymptotic notation, this is says that R is less than or equal to 1 minus H2 delta by 2 plus a little bit. Okay, that's what we had these two curves. We're going to pick this one because we'll be going. We had delta, this was R, and this is delta being equal to 1. Okay, 1. So the Gilbert functional bound is something like that. The Hamming bound something like that. It's not a straight line. So one time I have to draw it. It's something like that. It's a convex curve. And everything over here is not allowed. And everything over here is allowed. Okay. One thing I want to stress, so somewhere in the proof of either the game, recall, so we recall in the proof, both these proofs, we had used this fact. What had we used? We had used the fact that the volume n Pn is less than or equal to 2 power h2 Pn. Which proof did we use this? Huh? In the first one, you need this. But notice this proof we didn't actually both these proofs. We used this one in the first proof and this one in the second proof. H2P minus the low one. And in the asymptotic, while deriving the asymptotic version from previous statements, we use this form. But this proof, if you recall, somewhere in the proof of this, we used the fact that P was between 0 and half. In this proof, it's perfectly fine to do it because the P which is applied is d by 2, and d by 2 is certainly less than half. D is less than n, d by 2 is less than half. In the other direction, that's not true. That the other direction, so in other words, Gilbert-Wassermann bound. The Gilbert-Wassermann bound, okay, of course, gives you this thing. So you could ask, it gives you shows that they exist over here. You could ask even with, can there exist a code right somewhere over here with very tiny r? So that will be one question which we'll ask here. Do there exist codes, binary codes, which are with distance greater than half? Why is this a natural? Why is this a natural point? Over here, we try to answer this question. And the same thing for whether both these bounds have corresponding query analogs. You can write the query analogs for it. It will just replace. It will just replace the this 2, the binary entropy 2, not this 2. This 2 just comes from unique distance. The binary entropy 2 will get replaced with the query entropy. You'll still get two similar curves, but it's for the alphabet size q. And notice each of these are, when you're doing these asymptotics, we are thinking of the alphabet size as being fixed. It's one fixed alphabet size, like q equals 2, q equals 5, q equals 10, and then you're drawing the okay. So one question which we will address by the end of today's lecture very early on is, do there exist code over here? And we'll show that y half is a natural point for binary codes, and for query codes it will be 1 minus 1 over q. That will be the very natural. So let's begin with the first of our bounds, which is a Singleton bound. Actually, I don't know why. For historical reasons, this bound is called the Singleton bound, though Singleton was not the first person to do it. So it was actually proved by Joshi early on from ISI. Kingston in the Singleton paper from 1954. Joshi already had it in his paper in 1958. Singleton bound, and Joshi actually claims this is in a write-up of Komamiya, who was a Japanese coding theorist from a year before Joshi's result. So technically it should be called the Komamiya bound or the Komamiya-Joshi Singleton bound, but the Singleton bound is tough. In fact, for a long time, when I was in grad school, I thought Singleton was an adjective. I didn't realize Singleton was the last name of a person. It seemed so. It's like, for example, there's a number theorist who's called Factor. His last name is Factor. And there's a convex geometer, there's a very famous convex geometer whose last name is Ball. What's a singleton? So singleton is going to be an upper bound. It's going to be terrible bond, the way we will say. It's going to be a terrible bond. It's going to be worse than every single upper bond we do. Why do we look at it? I'll come to that later. But it's a very clean, nice bond. It's of course one of the earliest known bonds. So singleton bond is the following. It says for all NKD Q codes. Notice in singleton, I'm going to move away from the binary alphabet because the statement will be true for all Q, not just one. For all NK Q, we have K plus D. If you look at the sum, this can be at most N plus 1. This can never be. This is independent of Q. For every Q, if whichever alphabet you choose, Q doesn't enter into this at all. In the other bounds, Q entered into it, and you had to go for the QA entropy or something. Q doesn't make its entry into this at all. It just says the distance plus the dimension can never be larger than N plus 1. With whichever alphabet you use. And this whichever alphabet you use will be useful later on. We'll come to it later. So that's the bound. First, let's see the proof of this, and then see what asymptotically it means. So you're given some codes. So C is some NKBQ code. So C is some subset of sigma to the n. It's a where sigma is size K. And furthermore, we can assume because of the fact that C is actually size of C is sigma to the K. So it's some sigma K size. That's Q to the K. Sigma is a set. Size of sigma is Q. That's the thing. And from this, we want to derive the form. So what I will do is let's come up with a projection. Let's consider this following projection. From it's pi from the space of sigma to the n to sigma to the k minus 1 projection pi. And what does it do? It drops out all the first n minus k plus 1. It just drops them off. Formed by dropping all of the first n minus k plus 1 symbols. Okay. What does this projection do to C? So things in C are also going to get projected. What can you say about this? The size of C, notice, is larger than the set into which you are projecting. So what will happen? The pigeonhole principle will tell you two guys, there will exist two code words. So by PHP or whatever, there exists C1 not equal to C2 belonging to C, such that pi C1 equals pi C2. But then what does this mean? So where does C, you know C1 and C2 have to be distinct code words. They are far away from each other. So where does this distance have to come from? It can come only from the n minus k plus 1 part. It cannot come from the k minus 1 part. So you know immediately this says that delta of C1, C2 should be less than or equal to n minus k plus 1, and that's the entire piece. So D is less than or equal to. So the reason I'm doing it so slowly, it's a very simple proof. It's known long ago, but this notion of projecting the code and stuff is something we will see over and over again. In fact, there's a whole problem in your problem set. Just devoted to if I have an NKT4, can I get an N-1, N-1, T4? All of these are just part of projection and puncturing and this sort of things, just to get yourself comfortable with this. So the singleton bond here, so it's K plus D less than equal to N plus 1. Now, how do we write it in the asymptotic notation? So R plus delta is less than equal to 1 plus little o 1. 1 plus little o 1. And in the, so what does the singleton bound in the asymptotic notation? Singleton bound here for following in the asymptotic. Singleton bound, it's a upper bound for the singleton, right? So R plus delta is less than equal to 1 plus little o 1. Okay. So let's go back to that curve. So how does this one look? It's going to look like a straight line which joins that point and this point. So it's strictly worse off than the Hamming bound. Yeah, so but that's a singleton bound. So that we come to that discussion just now. So why did I even do the singleton bound when it's worse off than what we had already studied before? And as Peter has said, what we will see is there are actually codes that achieve the singleton bound. Now this should be ridiculous. So this picture is true only for a fixed alphabet. So for a fixed alphabet, these two curves will keep changing as the alphabet changes. The singleton bound never changes. It's the same R plus delta. Bound will remain same. So this red curve keeps going closer and closer to this one as Q becomes larger and larger. And in fact, so what we will show is the first code which we will study, which will be next lecture, the Reed-Solomon code, will be a code which will achieve the singleton bound. But it achieves this at a cost. It achieves this by having an alphabet size, which unlike anything we have studied now, is also going to grow with n. So far, we always studied at alphabet sizes, which were a fixed constant. They were 2, 5, 49. That was the basic alphabet size we got. Now, enough, when you do Reed-Solomon, we will consider alphabet sets which also grow as the code keeps growing. So that then you cannot compare them this way because all of these curves are drawn for a fixed Q. Whereas Reed-Solomon code, the family of codes itself talks about growing alphabet size. Therefore, even though for every fixed Q, the singleton bound is a useless bound because every other bound. When you're talking about large alphabets, these other bounds don't make sense. The singleton bound is what enters into the picture. And in fact, we will see codes, we'll see a whole family of codes that will achieve the singleton bound.
So for that, there will be no reason when we decide the code is.
1 second, singleton bound. So what I want to say is the following. For every fixed alphabet, singleton bound is worse than Hamming bound. And the reason is actually fairly simple. The Hamming bound is convex. Singleton bound is a straight line. You can check that there is a function, it will always be. For every fixed Q, it will be. But the point is, it's not fair to compare. So, but we will show, but surprisingly, ironically, whatever, surprisingly, people construct codes which meet singleton bound. Singleton bound, albeit over a growing alphabet. And they'll meet is they will not just meet r plus delta equals 1. They will meet p plus k equals n plus 1. They will meet it exactly in the resolvent code. Okay. So, and codes which meet this bound are going to be called maximum distance separable codes. These are called MDS codes. They are called an important family of codes. And we will see this. The first of them will be the resolvent code, which we will discuss in the next lecture. Yeah. In the sense, the Hamming bound, in the sense, this bound will hold. Rather, this, so this will be q power k, q power n, volume q. No asymptotics has ever set in so far. And the claim is, yeah, so what you're saying is true. So that should happen. So, but I don't know how to compare this against the, so I don't know how to compare this against the line, because I know when I draw it, I can draw this, when I draw this curve itself, already I'm assuming q is a fixed quantity and I'm doing some approximation with q being fixed. So we are talking about growing q's, and I have to be a little careful about. Yeah. Yes, yes. Yeah. The Hamming bound curve will tend to the line. The Gilbert-Wassermann also possibly tend. Yeah, Gilbert-Wassermann will also tend to the line. Yeah. Okay.
You're saying you would include the HQ of delta versus a linear?
No, it will not. So the Gilbert-Wassermann will not. The HQ of delta. So that you can actually write down. No? You are asking as delta goes to what? Delta
as Q would include the HQ.
So this I don't know. This I don't.
Is what you're saying when you say that the Hamming bound.
I do not know the Hamming. It has to go to the straight line. So I don't know if these asymptotics work. So you are changing the order of quantifiers here. So I don't know how it works. So what you have to consider are these two codes. This you can't look at the Hamming. You can't look at this red color thing, because you should not look at this red one. If you look at the gray part, not look at this. It's the gray one. This you can compare it against the Singleton bound, and certainly what I'm trying to say, possibly this is approaching this bound is approaching the Singleton bound as q is going larger. So this is becoming q, this is becoming q, and this q is becoming q. So it's possibly approaching the Singleton bound as q is going larger. Next, we'll now come to answering this question about, do there exist non-trivial codes beyond half, distance half? And this is the question that we had asked then. This will be addressed by what's called the Plotkin bound. Plotkin bound says that, one you can see is that I'll state it only for binary code. You can state it for larger alphabets also. In fact, problem set has a problem which asks you to do it for the query alphabet. So suppose b were greater than n by 2. Then what can you say about this code? I want to say, Plotkin bound says something quite drastic. It says, if that's the case, there can only be n plus 1 code word. The code word space doesn't go exponentially. Typically, you would like it to go exponentially in n. It says no. If you're going to, if the code word, if the things are really this far apart from each other, then you really can't put, there can only exist n plus 1 code word at most. So rate wise, this is a terrible code. Rate is at 0, basically, because you're going to divide. The rate is going to be the log of this divided by n. The rate is tending to 0. So it says once you go for things above half, you're not going to get any meaningful rate. You're not going to get any positive rate. That's the Plotkin bond. This one, by the way, these have query analog for it. Then you will not compare it to n by 2, you will have to compare it to n into 1 minus 1 over q. 1 minus, so these numbers 1 minus 1 over q is a natural bottleneck for distance, and Plotkin bound is what's going to tell you why this is a because beyond that, you will hardly see any code. The code will be a very sparse object. Okay. And the corollary of this will be for any d, size of C should be less than or equal to 2 times d times 2 power n minus 2d plus 2. 2d plus 1. Plus 1. So these are what is called the Plotkin bond. So the name Plotkin bond is not known in either of these forms, but it's stated enough. The first one is called the Plotkin bond. The second one, let's state the Plotkin bond. Let's write the Plotkin bond in the asymptotic notation. So what will happen if we write this in the asymptotic notation? So before we prove it, let's do that first. What are we saying? We're saying 2 power k is less than or equal to 2 power n minus 2d plus that 2. I'm going to take it up, so it becomes the 1 becomes the 2, and the log also, and the d also I'll take it up and make it a log 2. So we have k is less than or equal to n minus 2d plus 2 plus log 2d. Now we will divide everything by n. So that will be r. So what will we have? We have the following statement. That is r is less than or equal to 1 minus 2 delta plus a little over. So this tells you r plus 2 delta is less than or equal to 1. So for binary code, these are very, very far away from. If we go back to that picture. This picture, what's happening over here? This code, this form. Redraw the picture. So we had let's first draw. So this is delta equals half. And the Hamming bond is exactly this straight. Sorry, not the Hamming bond. The Plotkin bond is this straight line. That's just r plus 2 delta equals 1. The Hamming bond is a bond which starts off like that and then goes. So there's an initial region where the Hamming bond is better off than the Plotkin bond, and then the Plotkin bond beats it. And then of course you have the Gilbert bond, which is sitting below both these curves. Okay. So that's the state of affairs at this point. And this Plotkin bond, that first, in fact, the first item of Plotkin bond is stating that why this is a natural one. Okay. So let's these bonds. This one. So that's Plotkin. This is Hamming. Now let's go into the proof of the Plotkin bond. Let's first do 2, assuming 1. Let's go 2, assuming 1. So let's assume this one and use that to prove this object. Okay. And the main idea, once again, this is going to sort of use these projections and codes. So let's look at C. So C is some n symbol code, n bit code. Now, if we want to use 1, we have to look at codes which are only of distance in which the block length is less than 2D. We can't look at. So here this n could be much larger. We know that the code has the distance d. So if you want to even apply 1, we have to look at things which have just block length little less than 2D. Only then we can apply 1. So how do we do that? Let's look at the following thing. Let's just break this off. So this is 2D minus 1. And this is L, which is where L is n minus 2D plus. Now, for every A in 0, 1 to the L. So for every possible setting in the first L bits, we will look at the subcode CA. CA is those x's in C, such that x is of the form a comma y for some y in 0, 1 to the what are those 2D minus. So the code is take all those code words in C such that the first L bits look like A. It's just that part of the code space. Notice that CA is also a code. CA is a code, it's over a large alphabet N, but you can basically drop off the alphabets at L. Yeah, the first L symbols make, because all the code words share the same L things. If you look at a specific CA, all the first L things look the same. So actually the block length is only over here. And here and the whole distance has to come from these 2D minus 1 locations. So within each CA, it might be that CA has 0 code words. It might be that CA has just 1 code word, 2, but whatever you know, if it has at least 2 code words, you know that its distance has to be at most its block length plus 1, which is 2D. So the observation is, what is the distance of CA is at least D. If it has 2, it's at least D. If it has 1, certainly the distance is all the way, it's 2D, or if it has nothing, there's no distance is undefined, we'll take it to infinity. So in all cases, this is for all A. For all A. Hence by 1, size of CA is less than or equal to what? Its block length, that is 2D minus 1 plus 1. Fair enough. And that's how I'm using 1. Now let's conclude. What is C? C is just, size of C is just, by definition, it's the CA form a partition of the whole thing. Each one is of length 2D. How many of them are there? They can be at most 2 per L. That's the whole. That's the 2 power L times 2D. And that's exactly what we had here. Fine. So we need to prove that if D is greater than n by 2, then size of C is less than or equal to n plus 1. Okay. That's the proof which we show. And this is one of the places where now is the first place where so far we've been using the Hamming metric everywhere. It will be easier to prove this if you had the Euclidean metric on the code. So what we will do is we will take these code words. This proof, it's an interesting proof technique, it's a useful proof technique. We will take this proof, we'll take the embed the code words in R to the n. We'll take the code words are bit strings now. They are 0, 1 strings. We will embed them in R to the n such that we can then appeal to Euclidean. We'll do some sort of this embedding and take things which are far apart, which will make them continue to make them far apart, and we'll ensure that. And then we'll appeal to our Euclidean metric intuition to show that. So this is a case in which we're actually going to go. The technique is going to be go from Hamming to Euclid. And how will we do this? So let me see. By the way, you don't have to do this. There is an alternate proof of this, which is purely combinatorial. You can do the Plotkin mode, and this is the proof which is given in the problem that if you do all the parts, you will get a fully combinatorial proof, not the geometric proof, but we'll give a very nice geometric proof. Nice geometric proof. So we're going to embed. How we're going to do this embedding? We're going to first embed 0, 1 into R. We're going to take every bit and map it to this one. And what we're going to basically do is going to map a bit B to -1 to the power B. That will be the number. So in other words, 0 will get mapped to, so that is 0 will get mapped to 1, 1 will get mapped to -1. So this is what I call B tilde. So given B tilde is this. Okay. This is, and then extend it to all of it. 0, 1, n. I want to map it to Rn. So more precisely, if you have x1, x2, xn, n bits, what we'll just map it to is x1 tilde, x2 tilde, xn tilde. So you take a 0, 1 string, you map it to 1 -1 string. And the natural thing is take a 0, map it to 1, take a 1, map it to -1. Okay. What's the nice thing about this? The key fact is if delta of xy is d, what can you say about x tilde and y tilde? Actually, that's maybe this one. If I want to talk about now about the Euclidean inner product, this is just summation xi tilde yi tilde. What will this be? So let's look at what is summation xi yi. If the two bits agree, that contribute that product is 1. It's -1 into -1 or 1 into 1. It's 1. If the two bits disagree, its contribution is -1. Therefore, for every agreement, you will get 1. For every disagreement, you will get -1. Therefore, how many agreements are there? There are n minus d agreements. And there are d disagreements. So it's n minus d minus another d. So this is n minus 2d. This is an if and only if. This is d, this is x tilde, y tilde. The inner product between them has to be n minus 2. So what is this? So what's the quantity? What's this guy? This guy is just summation xi tilde, yi tilde. But notice that all our xi tilde, yi tilde are plus or minus 1s. Therefore, either this product is 1 or -1. When is it 1? Exactly when xi tilde and yi tilde are the same bit. It's -1 when they are different. That's exactly for measuring distance. So n minus d times they are the same because the distance is d, and d times they are different. So n minus d minus d, that's n minus 2. Now, but this will tell you something. What does this tell you? So give the original code word. So we started off with C. So let's start off with C, which is C1, C2, Cn. These are all the code words. Suppose. And then we came up with C tilde using this mapping. This is sitting in 0, 1 to the n. we went to C1 tilde, CM tilde. This is sitting in R to the N. Suppose these codes, we started off with the fact that furthermore you started that distance of C was greater than N by 2. What does that mean over here? Huh? If CICJ is negative, but every distinct, that is for all I not equal to J, Ci tilde, Cj tilde is less than 0. In other words, they hold an obtuse angle with each other. And of course, we also have for I equals J. What is this? This is N. We won't use this. Okay. That's what we have. Now, so I'm telling you, so this N just means that let's assume that they're unit vectors. I'm going to scale them. So I give you N vectors. I give you N vectors in N dimensional space, and they say they are all more than 90 degrees. Every pair is more than 90 degrees from them. Firstly, can you come up with such a configuration? Huh? With the so yeah, with N plus, what's the configuration with N plus 1? Let's do orthogonal. So let's take N to be 2. You're working on the plane. So I want to get as many things. So ideally the number should be 3. Can you get 3? 120, 120. So the vertices of a equilateral triangle or the simplex, same thing goes. We go to the underlying dimension be N, use the corresponding simplex, those points will be every pair of them will have the same angle and it will all be up to you. Huh? No, we will prove this now. So we will what we are going to show is size of C tilde is less than or equal to N plus 1. And notice this is tight because of vertices of the simplex in dimension. You can't improve this, and this is exactly the result which we want. Okay, so we'll appeal the geometric intuition to prove this. How does one go about doing this? There, by the way, just this geometric fact. So this is called geometric lemma. Yes. What am I saying? Z1, Z2, Z2. Rn such that for all I not equal to J, Vi Vj is less than 0. That's they hold an obtuse angle. Then N is less than equal. There's a nice inductive proof of it. What I will now give is actually I will give a geometric proof of how would you prove this. So let's assume otherwise. That is, there exists Z1, Z2, N plus 2, or even more. So we can say there exists N plus 2 vectors in Rn such that Zi, Zj is less than 0 for all I. What can we do with this? So I think we can do. So once you have vectors in N, and certainly something more than N, what is it that you can say? There is a linear dependency. In fact, linear dependency, we need N plus 2 for the linear dependency. N plus 1 is sufficient. So already we know there is a linear dependency among the N plus 1. So Z1, Z2, Z N plus 1 are in Rn and hence linearly dependent. That is, there exists lambda I zi, I going from 1 to n plus 1 is 0 for some lambda 1, lambda 2, lambda n plus 1, which is not the all zeros. Let's stare at this a little more. So some of the lambda i's are going to be positive, some of them are going to be negative. Let's partition this. Let's, without loss of generality, assume the first L of them are positive, the next all the way up to T are negative, and then the rest are all zeros. That's without loss of generality. Of course, this L and the next could all be, they could themselves could be zero. So without loss of generality, assume we have the following. That is, for the first I equals 1 to this I equal, there exists L, which is 0 less than or equal to L, which is less than or equal to T, which is less than or equal to n plus 1. There exists this one, such that the first I are the alpha, I want alpha i's to be positive, and also I want the beta j's to be positive. The first, these are the sum of the positive guys. I'm just reordering them because this is the first L guys. This is equal to beta j, zi, j going with j going from L plus 1 to T. So from L plus 1 to T, these are the negative guys. So I'm moving them this side. Therefore, now beta j is still positive, and the rest are all zero. So I'm just rewriting the above equation in this format. But notice L could be 0. So what should be L plus T equal to? No, this is L plus 1 to T.
No. Which one? There exists L is equal to T. I am saying that L and T between 0 to n plus 1 and that sum should not be exceeded.
The indexing is going from L plus 1 to T. It's not going, I'm not saying these are L in number and these are T in number. And furthermore, one other thing I should keep is L and T here. At least one of them is positive. This is not, because we know it's not the non-zero component. Either L, and without loss of generality, we can assume L, because if one of them is this one, you can say, so I can actually make, so I can make this. I can assume that L is the guy which is positive. Okay, so this is some non-zero combination. This could be a zero, a combination of 0 is. So let's look at basically there are two cases which L equals T. That is, there is nothing. Sorry, let's look at the other case. L is not equal to T first. That's the easier case. And L is less than T. Then let's just define Z to be this quantity. What's the inner product of Z with itself? It's certainly a non-negative number. But on the other hand, what is this? This is I going from 1 to L, J going from L plus 1 to T, alpha I, beta J, Zi, Zj. It's just this. And each of these is negative. These are positive numbers. Therefore, this is less than 0. That's a contradiction. So L cannot be less than 0. So L has to be equal to T. All the signs should be the same. So then let's go to that. We haven't yet used one fact. What have we not yet used? We haven't yet used N plus 2. Yeah. So this is the assumption, no? Zi, Zj's are all negative. That's the geometric lemma. That is, they all make up this angle with each other. And they yeah, some of the negative terms, and at least, yeah. both are, there's at least one alpha I that is positive and one beta j that's positive. That's why we're using L less than B. Therefore, there will be at least one negative term in this. Could be more negative, but that's so. This will not be true if L equals C, because then every beta j is 0 and you won't get this. Now so far we didn't use the fact that Zn plus 2, otherwise the proof would have been done with Zn plus 1. We have to use Zn plus 2. So now let's look at. So now notice that because n equals 3, we know that Z itself is equal to 0. Z is equal to 0. Therefore, let's look at Zn plus 2's inner product with Z. What is this? This is 0 because Z is 0. But on the other hand, every Z involves only guys below it. So every inner product will be this one, and all the coefficients are positive. Therefore, this is just summation alpha I, Zn plus 2, Zi, I going from 1 to L, and this is less than 0. In either case, we have a contradiction. Therefore, so this is basically the fact that there are multiple ways to do this proof. In geometry intuition, that basically you have more than n plus 2 vectors, at least 2 of them have to be close to each other. You cannot have all of them making up your value. You just resorting to that, and Plotkin's bound is just taking that, transferring that to the Hamming method. So Plotkin, the idea is this basically this map. The key thing about Plotkin over here is this very nice mapping. And you see in Fourier, there's a lot of places where we take the actually the Boolean world, map it to the real world, and do this, and this is basically what the high underlying thing within Plotkin, and then Plotkin is appealing to the geometric lemma to conclude the final. But ends the So yeah, so what can you do for the pure version? The pure version, what we will do is we will put it to the, instead of -1, we will take the complex roots of the few roots of unity, and we'll transfer the bit b, the symbol b to omega to the power b, and put it that way. And so that's what you should see when you simplex, and this proof will work. So it's there, this proof is there in the, I think it's there in the full formula Russell, and you can just sort of calculations, but it's the exact same proof. Exact same proof. It's a little more messier than this, but it's the same proof. But this is not the proof which I'm asking you to do in your problem set. The problem set is a combinatorial proof of the Plotkin. These are both this proof and the pure analog, which I said are geometric proofs. The problem set is a combinatorial proof of the same sign. Of the final fact, not of the intermediate geometric lemma of the Plotkin problem. Okay. So where are we in the picture of this is the picture that we have. So we had there's a Singleton bond which I'm not drawing, but for a fixed cube, that's always worse than any of your bond. It's that line joining this point and that point. There's a Hamming bond, there's a Plotkin bond, and there's a Gilbert bond. Now, it's sort of odd to work with these. So you notice that in certain ranges of delta, the Hamming bond is better. In some ranges of delta, the Plotkin bond is better. So what I would like to now know is, can I come up with a single bond which outperforms, which is at least as good as the Hamming bond and the Plotkin bond? So it's always sort of below this over here. Can I get this? Can I achieve something which does as good as the Hamming and Plotkin? And that's going to be our final bond, which we will do. It's called the Elias-Bassalygo bond, which is a bond which is going to be strictly better off than both the, not strictly, it's going to be better than the Hamming bond and the Plotkin bond at every point. Therefore, it will be a curve, it will be another convex curve starting from there to here and lying below the Hamming bond.
So by a single bond, I can take the minimum.
You can take a minimum. It's one nice convex curve. This is not a convex curve. One nice convex curve. Yeah, you can take the minimum works. It's one nice convex curve, and it's one single argument to talk of both. This one. The question is, Is there a nice? So yeah, you can question what I mean by nice in this. So nice is possibly convex nice bound that performs as well as Plotkin and Hamming. Question asked, and the answer is yes, and this is the next point. Sometimes it's also called the Elias-Bassalygo Johnson bound because there will be a bound due to Johnson, which is useful in proving this bound. So what is the bound for this? So how did the Hamming, so let's recall the proof of the Hamming bond. How was the Hamming bond proof? So you had these coordinates in this ambient space, where 0, 1 to the n, and you put in these balls around them. And you put in balls so that no two balls are intersecting. These are disjoint balls, so you could put balls of radius at most b minus 1 by 2, the floor of this. And then you said the total volume of all these balls should be less than 2 par n. This was what gave you the Hamming bond. Let's change it a little bit. Let's do the following thing. So you have the space 0, 1 to the n. You have the code word point here. Suppose now, so previously we drew balls of radius delta by 2, fraction radius delta by 2. Now let's draw fraction radius, slightly larger radius, say tau. I'm going to draw tau things of them, but I'm going to give you previously delta by 2, the balls of radius delta by 2 had the guarantee that any two balls had no thing in the intersection. But suppose now we give a guarantee that for every code word C in C, the ball C and tau n, if you draw a ball C and tau n, and you ask how many code words are there in this. Previously, if tau was chosen to be delta less than delta by 2, this intersection was 1. Suppose this intersection was L, at most L. So suppose there exists a tau which is in 0, 1 and L which is in the positive integers, such that this is true. Let's try to redo the Hamming bond under this assumption. So what will be the Hamming bond? You have the same thing now. You have size of C into volume 2 n tau n. That's the total volume of all the balls. What will be this less? It has to be less than L times 2 par n, because a particular point can be counted at most L times. So let's write this in the asymptotic notation. So this will be K plus H2 tau is less than or equal to 1 plus log 2L. That's what log 2L by n, no? But no, log 2L, sorry, there is an n missing over here. Therefore, you have R plus H2 tau is less than or equal to 1 plus this log L by n. So as long as L is something which is, say L is this polynomial. This L could be not 1, 2 or something. Suppose I put n cube or n power 4. This is an insignificant number. It just vanishes out. It becomes a plus little o1 term in the bound. In fact, L could go as large as 2 to the little o n. As long as L is 2 to the little o n, it's not exponential. It's just below exponential. Then we have such a form. Okay. So what I want to observe is this L doesn't really matter. Having this extra L, so we could have grown the balls in the Hamming bound to much larger. If we can show that if you go a little larger than delta by 2, you begin getting intersections, but the intersections are of bounded size. They never go exponentially large. So if you keep expanding up to a particular point till which the bound L is. So the observation is if L is, as long as L is 2 to the little o n, we still get R plus H2 tau is less than 1 plus little o 1. So in that sense, so basically we are replacing the having put a delta by 2 over here, we are replacing it possibly a larger tau. Question is such a tau exists. So right now so tau and L come as a pair. Tau and L come as a pair. What's the property of the pair? The pair is such that if you draw a ball of radius tau around any code word and look at the number of code words in that ball, that should be at most L. For example, an instantiation of this is tau being delta by 2 and L being 1. So that will tell you. But I'm claiming that that was one extreme case of this. You could have set tau to be a much larger quantity as long as the corresponding L was sub-exponential. It will still give you a bound. It will give you R plus H2 tau. So for every choice of tau and L, as long as L is this, we do get this corresponding bound. The question is, can I choose tau? Can I get a pair tau and L for which L is 2 to the little o 1 and tau is larger than delta by 2. As I keep going larger than delta by 2, this number becomes larger and it's a better and better bound over R. So it's certainly this consumed within it the Hamming bound. Hamming bound is one instantiation of this when I choose tau to be delta by 2 and L to be 1. So I can write this as a max over, I can write this over all possible tau and L pairs such that L is 2 to the little o 1. I can write this. One such bound is the Hamming bound. So this is the idea of Elias-Bassalygo. And the question is, does there exist a tau for which this is meaning? For which even if I go above delta by 2, can I still put a bound on the number of code words in that ball? By the way, this is what is called. So what's happening here? Previously, we were talking about if you go up to what was the point of delta by 2? Delta by 2 said that if you make at most delta by 2 corruptions, then you can uniquely say this is the code word you are from. So this was the Hamming sort of this one. Hamming said if Hamming errors, if you made at most delta by 2 errors or flips, then this is the word you should have come. Now we are going to make errors more than delta by 2. You're going to make errors, say tau errors. If you have this, what you're saying, I do not know this is a unique guy, but I can tell you there's a list L of guys. You possibly are one among this list here. And if you have other side information, go and figure out which of this L guys you want. So you can sort of change the problem. So this is sort of introduces the notion of list decoding. It's no longer as opposed to unique decoding. So, and we will see list decoding. List decoding will make its entry multiple places, and finally we will study list decoding will actually come up with algorithms for list decoding eventually. But list decoding will sort of make its head, even though we don't want to never came up with studying it, we're trying to study some other place, list decoding. And just like it made its entry right now, it is stating that it is conceivable that you can ask for these questions beyond the unique decoding radius, that is beyond delta by 2. You can say, suppose you made more errors than your channel is really noisy. It flips more than delta by 2. Then can you do something meaningful even at that point? The previous definition said if you're working with unique decoding, you say if the channel is going to be that noisy, I'm going to give up my hands. But this says no, even in that case, the code had this property, you could possibly recover the L code words and then say you use some other information possibly to eliminate to find out what is the right message. I can give you a short list. So as long as L is sub-exponential, for algorithmic purposes, you want L to be polynomial in size. The list, it should be outputting a polynomial size list. Only then is it useful. If it's going to output something which is super polynomial, I don't know how to work with this list. So list decoding is a useful thing. So you try to we'll very much keep asking these questions. Up to what point can you make this ball radius go from delta by 2 tau all the way, such that the list is only polynomial in size. Okay. And you can ask this for every single code. You can ask this. What Johnson proved, actually, it's not yet why it is Johnson, but it's called the Johnson radius. Said that for every code, if I know the distance delta, there is another number tau. That is, for all codes C, which is N, K, delta N. What? Let's do binary codes. You can go up to the following radius, which I call J2 delta. That's for the Johnson radius. It differs, and the 2 is because we are working with the binary alphabet. This number changes for the other alphabet. Johnson showed this number 1 minus square root 1 minus 2 delta. It seems a weird number, but we will shortly see in a short while. This is a number always larger than delta by 2. Actually, it's not hard to see it. 1 minus 2 delta. Square root of 1 minus, so let's do that on the side. So 1 minus x power half, I claim it's always less than 1 minus x by 2. Agree with that? Just square both sides. So 1 minus x is less than or equal to 1 minus 1 plus x squared by 4 minus x. There's always a positive quantity here. This is always fact that's true. And that will imply that square root 1 minus 2 delta is always less than or equal to 1 minus delta. Therefore, half 1 minus square root 1 minus 2 delta will be 1 minus delta. So delta, so this is always greater than or equal to delta. Huh? No. This is for delta. So we are working with codes. Plotkin, we understood Plotkin. So delta is always less than half. We're never talking about things codes which are more than half. Yeah. Things are all going to make sense. So delta half. There will be a corresponding query version of it where delta goes from 0 to 1 minus 1 over cube, and this number will be well defined only if delta is less than 1 minus 1 over what?
So code switch, delta Plotkin norm.
I didn't. Why is the Plotkin board coming in the picture now?
No, simple data.
So for delta greater than half, so the point is, it might be defined, but the point is the code is such a useless code. The code has so many few code words. So you can possibly do it, and the code has only n plus 1. Just go over the whole list, find out which is the closest guy. It's not a hard problem in those cases. So it's not interesting. The code space itself is polynomial. So you can probably just, it's not that it's not doable, it's just trivial. So the interesting question happens only when you work with in this regime, because when you go above half, the code becomes becomes trivial, and you can run, because you have the entire set of code word space is a polynomial set. In fact, the linear set, you can do every possible algorithm you want. Only because of the and what I just defined the quantity. What Johnson shows is up to this radius, L for every code which has distance delta is polynomial. That is basically he shows for all C in C, the ball of C J2 delta N intersection C is at most polynomial. So this is true for every single code. Every single code you can expand this radius from delta by 2 to this number tau, which is always larger than delta by 2. Notice it becomes very close to delta by 2 when delta goes to 0. So this inequality has become very tight. The thing is x squared by 4 when delta goes to 0, this is a tight inequality. So when for delta very, very close to 0, these two bounds will be the same bound. But otherwise, this is always a better bound. And once you have the Johnson radius, we will prove the Johnson radius, possibly not in this picture. We will prove multiple. This will be a very important fact. We will give multiple proofs of this, and this will keep making its entry again and again over the course of the course. But an immediate corollary of this is the EV bound. Which says R plus H2 J2 delta. This doesn't equal to. I could have replaced the Hamming bound, it was delta by 2. I can replace it with J2 delta because J2 delta is a number. Notice that for codes, for different codes, it could be different. They could be even a large. All the Johnson radius is guaranteeing is up to this point, it's polynomial. It doesn't say beyond this polynomial point, it's not polynomial. It could be that it continues to remain polynomial beyond this point. But it says for every code, up to this point at least, you could grow these balls from size delta by 2, you keep going them all the way up to this point, up to J2 delta, so that the number of code words you see will still be a polynomial for every code, as long as the code you began with had distance delta. Okay. So we will prove the Johnson radius. We'll prove the Johnson radius, we'll prove that bound. I'll actually give you more intuition why that number is. So, just for the I'll give you more intuition why that's a natural number that comes. For two reasons. One, we'll say that the calculation will pop out very naturally. Other, it says you cannot do better than this if you want such a universal system. We are taking that. Give me a code with distance delta. I want to give you this one. So we will construct code with distance delta, for which if you go just beyond this radius, there will be exponential. But that's not true. There might be code words, there might be codes for which even beyond this, actually it is still polynomial. What we'll show is if you want such a general statement, for all that you know about the code is the distance, and you want the largest list decoding radius, the Johnson radius is the best radius one can come up with.
Maybe there's nothing to do with that, but this term looks not like some activity or noise integrity thing that we see.
It will come, the proof will come. When you see the proof, these will be very similar objects. You will see this. You will see this. How, I do not know exactly how, you will see it, the proof of it will come. Right? Today we will not do the proof. I will try to see if I can do the proof in the beginning of next lecture. But let's see the consequences of. So what I'm trying to say is, this is extending the Hamming bound to this bound. And certainly now notice that this bound is better than the Hamming bound. So that already tells you it's better than the Hamming. So basically, this number is larger than delta by 2, therefore, and H2 below half is still is an increasing function. So this number is larger than H2 delta by 2, therefore, this is a better bound than. And I also want to say, so by design, that's the mean bound which we wanted to have. That's the key bound which we wanted to have. By design, EB is better than Hamming. What about compare it against Plotkin? So I'll take 5 more minutes. I'll just do this comparison. You don't have to. Go back to that curve which we had. A different curve. So Plotkin was R plus 2 delta is less than equal to 1. Hamming was R plus H2 delta by 2 is less than equal to 1. But rather these are the lines, so just equality lines. And now I'm asking the new curve which I want to draw is the EB bound. This is R plus H2 half 1 minus square root 1 minus 2 delta equals 1. It's the curve below this. The question is, where is this? One thing which you have seen is always below the Hamming curve. That's what we have seen. I want to ask how is it compared to the Plotkin curve. So let's look at the two extreme points, because that's a straight line. So if I know what, firstly, you should stare at this and see if this is a convex thing. If it's convex and it intersects the Plotkin bone on the two intercepts, then it has to be below the one. So what is it at R equals 0? So let's look at delta equals 0 first. Delta equals 0 will be, this will be exactly, what is it? Delta equals 0, it's H2 of half, it's R equals 1. So that's 1, 0. So that's the point over there. Now at R equals 0, this one has to be equal to 1. For that to be 1, this number has to be 0. H2 of half should, the H2 of half is 1. And this number to be 0, delta should be half. Therefore, it's exactly this. Therefore, this curve is, actually between. So the EB bound is this violet curve, which is below the Plotkin curve and the Hamming bond, and that's better than either of them. Let me do it, and by convexity argument. EB is better. Okay, let's do a couple of small calculations. So we have checked convexity, we looked at delta equals 0 and delta equals half, these 2 points. Let's look at what happens around 0 and around half. So what happens when delta is approaching 0. Then we saw that J2 delta, we already saw that this approaches delta by 2. The calculation which we saw above is saying it approaches delta by 2. So this looks very much like the Hamming bound at that point. So at the top end, when delta is 0, it looks very much like the Hamming bound. Now let's look at delta equal to half minus epsilon and epsilon going to 0. Let's look at that regime. So these are two different regimes I'm going to be considering this. So at this point of time, we have J2 of half into 1 minus square root 1 minus 2 delta. So I'm going to put delta itself as half minus epsilon. So what will this be? This will be 1 minus 2 epsilon over here. So with that 1, it just becomes 2 square roots, So this is just J2 of half into 1 minus square root 12. Okay. So, and what we are actually interested in is that binary entropy at this point. Sorry. What we are actually interested in is the binary entropy at this function. So we are interested in binary entropy very close to half. So this is just an aside. If you look at H2 of half minus alpha, then alpha is very small. So you do the Taylor expansion of this one. What you notice is this is actually theta alpha square. In the Taylor expansion, if you notice it, you expand the binary entropy function for around half, you'll notice that it won't have a constant term, it won't have a first order term, it will have only the second order term. And that will be alpha square, and the rest will be this is for very small alpha, for small alpha.
It will be a constant. It's not half in one.
Huh?
H2 value of it's not half in one, right?
No, 1 second, what am I trying to say?
If it will be two of half one,
So I'm saying, okay, what I'm asking is it 1 plus
1 minus
1 minus, how much is it smaller than 1 minus? So it will be the constant term, and I want to say that the constant term will be there, which will be 1. The degree 1 term will cancel the contribution from alpha and 1 minus alpha. So half minus alpha and half plus alpha will sort of symmetrically cancel out. And the next thing will be the degree 2 term, so it will be like 1 minus theta alpha square. So because of this, what do you get? Huh? Order. So this is order epsilon. So sorry. H2 of this one will be 1 minus order epsilon. Therefore, the bound on rate you get over here, you are going to get the rate is greater than or equal to, the rate has to be, rate is order epsilon square. There will be a 1 minus epsilon square. Sorry, just order epsilon. Okay. So here you get the rate with order epsilon. This is what the EB bound. EB bound is giving you. And here what did we get? Here we get what the rate is less than or equal to 1 minus H2. This is almost the same as H2 delta by 2. So that is roughly 1 minus delta by 2 log 1 over delta. This is what we get it from. And there are some other terms here. The 1 minus delta terms will not matter here. This is the dominant term over here. So it says rate is at most so much. These are all upper bounds on the rate. Let's look at what happens achievability wise. That's what Gilbert-Wasserman gives at both these ends. What does Gilbert-Wasserman say? Gilbert-Wasserman says R is greater than or equal to 1 minus H2 delta. So it says R that there exists a code C, which is that R is greater than 1 minus delta log 1 over delta. So it says R, there exists one code with this, right? But no code can have more than delta by 2 log 1 over delta. And there's still this gap. We don't know which is the right way. Even at very close to delta, the delta being very small, we do not know which is the right thing. Either EB is right or Gilbert-Wasserman is right. So it's open. This is open. Which is correct. Of course, it's true for the entire regime, but I'm just focusing now on one end of the curve. Delta equals 0. Even there, we do not know which is correct. Let's go to the same thing in this regime. What does Gilbert-Wasserman give you over here? Gilbert-Wasserman gave you R greater than or equal to 1 minus H2 delta. Delta is half minus epsilon. So it's 1 minus epsilon squared here. Therefore, you'll get R is, there exists a code C, so that R is omega epsilon squared. So you get a code with rate epsilon squared, there you get a code. No code can have a thing better than. So you're getting a code with rate epsilon squared. There you're getting the no code can have rate better than epsilon. Now there's a quadratic gap between the two. You can ask which of them is good. Therefore, what is known is actually the answer seems to be closer to this. So there is in this case, there's an improvement called the LP bound, linear programming bound, due to MRRW, which shows that R is actually order epsilon square. It doesn't get you exactly this. It gets you epsilon square log 1 over epsilon. So it's a slightly long, it adds quantity to this. This is the close to the half regime. No, these are all interesting questions. So right now, so huh? No, this is a lower bound. This is a lower bound. It's an improvement over. So that improvement is order epsilon. This is also a lower bound. It gives you an upper bound on the rate. So it's a lower bound one. So it's this is the MRRW from the late 70s. It hasn't, and that's more or less the best that we know. So whether it's okay, so I want to conclude this discussion because next onward we will not talk about bounds on codes. So the Johnson radius is not bound to put. So there is the what do you call, there's the Gilbert-Wasserman bound, which is the best achievability which we have. We saw the Elias-Bassalygo bound that has been improved by what's called the LC bound. There is another curve sitting completely below the EV bound, and it shows that GB is close to tight, the region close to half, because GB gives you omega epsilon square, this gives you epsilon square log 1 over epsilon. It shows that GB is close to being tight. But let's just focus on the regime around half. There is the LP bound which says the code cannot have rate better than this. Then there's the GB bound which says there exists such a code. And then there's a question, but notice the GB bound is not an explicit code. But there's another code, can you come up with an explicit code? And there we are even worse off than, we don't even know how to do epsilon square. A couple of years ago, we were able to do epsilon square by log 1. So there are these three sort of things. There is what can be got explicitly, what the GB bound achieves, what's the best upper bound, and all these three is open, where the truth lies among the three of them. What was your last? Huh? Yeah. So it's epsilon square over log 1 over epsilon. So in the sense that there will be there's an explicit code which gets to epsilon square log 1 over epsilon. GB bound says it will go up to epsilon square, and then the upper bound says it epsilon square log 1 over. So these are all off. They are off by log 1 over epsilon factors from each other. It might be polylog 1 over epsilon factors. This one is log. I do not know if that one is log or polylog. So there are these three things. What can you achieve as an explicit code? What is there a code which is a GB bound, and what's an upper bound? And our understanding to this date, this has been more than 50 years or so, we still do not know, even forget about the entire GB curve, even at the regime close to half, we do not know which is the right. And it's a big open problem here. And this half and epsilon, I think I'm making a lot of us here. These are these are identical to what are called epsilon bias spaces. These are extremely useful in theoretical computer science. Most likely a second problem set will show one of the applications of epsilon bias spaces. Just if a code has distance half minus epsilon, it means something for us, and we'll see what it means. This will be in your second problem. So with this, we conclude the discussion on bounds of codes and go to the next lecture. We will start off with trying to prove the Johnson radius, and then we'll go to the one code which we use to rule them all, which will be the read-solvent code. We'll take the read-solvent code, and the next 3-4 lectures will be based on the read-solvent. So.